Imagine that you are standing in a quiet room. You are holding a single perfect crystal in your hand. It is cold and dense, the size of a sugar cube, and inside it, trillions upon trillions of atoms are arranged in a flawless, repeating grid like a cosmic honeycomb. To the naked eye, the crystal is perfectly still, utterly silent. But if you could zoom in past the visible, past the microscopic, all the way down to the scale of individual atoms, you would see something astonishing. You would see chaos. You would see a symphony of motion. The atoms are vibrating. They are shaking, twisting, and jostling against each other in a frantic dance that never stops, even at absolute zero. This is the hidden life of matter, the ceaseless quantum jitter that is the heartbeat of the solid state. And here is the thing that keeps physicists up at night. That motion is not random. It is governed by some of the most profound and unbreakable laws in the universe. The atoms in that crystal are not just shaking back and forth, they are also spinning. They carry a fundamental property called angular momentum, the same property that keeps a figure skater twirling or a planet orbiting a star. And in a closed system, angular momentum can never be created or destroyed. It can only be transferred, traded like cosmic currency between different parts of the crystal. But how? How does the spin of a single atom get passed along to its neighbor? How does a vibration become a rotation? And how does that rotation become something else entirely? For more than 100 years, this was one of the deepest mysteries in condensed matter physics. And just last month, a team of international researchers finally cracked it open. And what they found was so bizarre, so counterintuitive, that it forced them to rewrite the rules of arithmetic. They discovered that inside a crystal, 1 plus 1 can equal -1. Let me take you back to the beginning. The year is 1915. The First World War is raging across Europe, but in a quiet laboratory in Germany, two of the greatest physicists of the age, Albert Einstein and Wander Johannes de Haas, are conducting an experiment that will echo through the next century. They are investigating the connection between magnetism and rotation. They take a metal cylinder, suspend it on a thin wire, and magnetize it. When they change the magnetization, something remarkable happens. The cylinder begins to spin. The electrons inside the metal, each one a tiny spinning magnet, are transferring their angular momentum to the entire object. It was a stunning demonstration that the quantum world and the macroscopic world are not separate. The spin of a single electron is connected to the rotation of an entire cylinder. This was the Einstein-de Haas effect, and it proved that angular momentum is conserved across all scales, from the subatomic to the everyday. But there was a problem. Einstein and de Haas could see the effect, but they could not see the mechanism. They knew the spin was being transferred, but they had no idea how it traveled through the material. Was it passed from atom to atom like a baton in a relay race? Did it flow through the crystal like water through a pipe? For 100 years, the question remained unanswered. Researchers could measure the input, the change in magnetization, and the output, the mechanical rotation of the cylinder, but the journey in between was a black box. No one had ever directly observed the transfer of angular momentum inside a solid, that is, until now. An international team of physicists from the Fritz Haber Institute of the Max Planck Society, the Helmholtz-Zentrum Dresden-Rossendorf, and universities in Jülich, Tel Aviv, and Eindhoven decided to take on this century-old challenge. They chose a material called bismuth selenide, a crystal with a very special structure, and they built a machine that is, in many ways, the most sophisticated strobe light ever created. They hit the crystal with an invisible, ultra-intense pulse of light, a terahertz laser pulse with a very special property. The light was circularly polarized. Imagine the electric field of the light wave rotating like a corkscrew as it travels. This rotating electric field grabbed hold of the atoms in the crystal and forced them to move. It pushed them, literally, into a circular motion, making the atoms vibrate not back and forth, but around and around in tiny, perfect orbits. Now, this is where it gets interesting. The researchers were not just driving one vibration, they were using a second ultra-short laser pulse to probe a different vibration in the crystal, a partner that was coupled to the first. They wanted to see what would happen to the angular momentum when it was transferred from one type of atomic motion to another. They were watching the invisible baton pass from one runner to the next, and what they saw was nothing short of a shock. The initial atomic motion, the circular vibration driven by the first laser pulse, carried a certain amount of angular momentum in a certain direction. Let us say it was spinning clockwise. When that angular momentum was transferred to the second higher frequency vibration, something impossible happened. The direction of the rotation reversed. The second vibration started spinning counterclockwise. The angular momentum did not just move, it flipped. It was as if you threw a baseball with a clockwise spin, and when it hit the catcher's mitt, the mitt started spinning counterclockwise. It defies everything we know about how spinning objects behave in our everyday world. But here is the even crazier part. The researchers calculated the numbers. They measured the angular momentum of the first vibration and the angular momentum of the second vibration, and they discovered that the two units of angular momentum in the first vibration combined to create a single unit of angular momentum in the second, but in the opposite direction. Mathematically, it was 1 plus 1 equals minus 1. Now, if you show that equation to a banker, he will call the police. If you show it to a physicist, her eyes light up. How is this possible? How can two positive spins add up to a negative spin? The answer lies in the geometry of the crystal itself, in what physicists call rotational symmetry. And imagine you are standing in a room full of mirrors. You raise your right hand, but your reflection raises its left hand. To the outside observer, your right is its left, and both are completely valid movements. Inside the crystal lattice of bismuth selenide, certain rotational states are physically equivalent even though they rotate in opposite directions. The lattice is like a grid, and the atoms are locked into positions on that grid. When the angular momentum is transferred from one type of vibration to another, the geometry of the grid imposes a new set of rules. The only way for the angular momentum to fit into the new vibration is to flip direction. The researchers call this an Umklapp process. It is a German word that roughly means to flop over or to turn inside out. The angular momentum does not just transfer, it folds back on itself, emerging as a rotation that is twice the frequency and moving backward. Now let us pause for a moment and appreciate the sheer elegance of this discovery. Olga Minakova, the doctoral researcher who was the central experimental physicist on the study, said, "I find it extraordinarily elegant how the laws of physics are directly dictated by the symmetries of nature." And Sebastian Mehrlein, the group leader who led the study, added, "For me, these are exceptionally exciting results. We have discovered something fundamentally new that will hopefully make its way into the textbooks. This is what science looks like when it is working. It is not about confirming what we already know. It is about finding the cracks, the anomalies, the places where our intuition breaks down. And this discovery is a crack that could lead to a revolution." Because here is the bigger picture. This is not just about watching atoms spin. This is about understanding the fundamental nature of magnetism. Magnetism is, at its core, the alignment of spins. When you magnetize a material, you are lining up the angular momentum of billions of electrons. But how does that alignment happen? How does the spin of one electron influence the spin of its neighbor? It happens through the lattice, through the very vibrations that the researchers were studying. By directly observing the transfer of angular momentum between lattice vibrations, the team has provided an important foundation for understanding how magnetism stabilizes and equilibrates in solids. This is the microscopic machinery of one of the most important forces in the universe. But the implications go far beyond fundamental physics. This discovery opens the door to a whole new way of controlling materials. The researchers succeeded in selectively controlling the rotational direction of atomic circular motions using ultra-strong laser pulses. They are not just observing nature, they are manipulating it. They are using light to write instructions onto the crystal, telling the atoms which way to spin. And that has enormous implications for technology. Think about the computers we use today. They store information in the charge of electrons in tiny capacitors that are either full or empty, but charge-based computing generates heat. As we pack more and more transistors onto a chip, that heat becomes a fundamental limit. We are approaching the end of Moore's law, but what if we could store information in something else? What if we could store it in the spin of an electron? That is the field of spintronics. Spin is a quantum property. It does not generate heat. It can be manipulated with light, and it can be transferred through a crystal in ways that we are only beginning to understand. The ability to control the angular momentum of lattice vibrations with terahertz lasers could lead to a new generation of memory devices that are faster, smaller, and vastly more energy efficient. We are talking about computers that do not get hot, that process information at the speed of light, and that store data in the quantum dance of atoms. And here is the part that Richard Feynman would have loved. Feynman was a man who believed that the best way to understand something was to play with it, to build it, to see it with your own eyes. He once said, "What I cannot create, I do not understand." And this experiment is a masterpiece of creation. The researchers did not just observe the transfer of angular momentum, they created it. They used light to force atoms onto circular paths. They used a second pulse of light to watch the transfer. And they discovered a rule of arithmetic that does not exist in any textbook. They created a new piece of physics. Now, I want you to think about the scale of what they did. They are working with atoms, which are smaller than anything you can see. They are working with vibrations that happen in a trillionth of a second. They are using lasers that are so powerful they can bend the rules of quantum mechanics. And yet, the principle they are investigating is the same principle that keeps a spinning top upright or a planet in orbit. Angular momentum is one of the most fundamental quantities in the universe. It is as basic as energy. And the fact that we are only now, in 2026, beginning to understand how it is transferred inside a solid is a testament to the complexity of the universe and the ingenuity of the human mind. So, the next time you pick up a magnet, or look at a spinning top, or watch a figure skater twirl, remember that you are seeing a macroscopic manifestation of a microscopic mystery. The spin of a skater is connected to the spin of an electron. The rotation of a planet is connected to the rotation of an atom. The universe is a vast web of spinning things, and the angular momentum flows through it like an invisible river, forever conserved, forever transforming. And now, for the first time, we can watch that river flow. We can see the whirlpools and the eddies. We can see the atoms spin in one direction, transfer their momentum, and spin back the other way. We can see 1 plus 1 equal -1. That is the beauty of physics. It is not a set of rules written in stone. It is a living, breathing conversation with nature. And every time we ask a new question, nature gives us a new answer. Sometimes that answer is exactly what we expected, but sometimes it is something so strange, so unexpected, that it forces us to rethink everything we thought we knew. That is what happened here. And that is why we keep asking. That is why we keep building better lasers, better detectors, better experiments. That is the spirit of Feynman's Curiosity Lab. We do not just learn about the universe, we poke it, we prod it, we shine light on it and watch what happens. And when it surprises us, we smile. Because that is when we know we have found something real.